All right, we're going to take a look at the auto ionization of water. I showed you before how H2O is amphiprotic. It can act as an acid and a base. Well, this leads to the auto ionization of water. All right, let's see here. So basically, I'm just writing it this way. You could put 2H2O, but I'm just writing it out like this. We have pure H2O. So we have distilled H2O. That's what pure H2O is, distilled water. There's nothing else in it. What's going to happen is you're going to have one H2O molecule is going to act as an acid, the other one will act as a base. And we're going to end up with in our water. This is exactly what happens if you have distilled water, right? And again, this is called the auto ionization of water. For this reason, now we're going to go through the amounts of these actually. We're going to see that this concentration, if you have 1 liter, this concentration is 1 times 10 to the minus 7, okay? So it's really small. That one also is going to be 1 times 10 to the minus 7 at 20 degrees Celsius, 25 degrees Celsius. So really small concentrations of these are in there, really small. That's why water is a poor conductor of electricity. Like lake water or your tap water can conduct electricity because it has ions in it. It has different minerals, chlorine, different things in there. So that can conduct electricity. But actually pure water is a very poor conductor of electricity for this reason. These concentrations are really low. So again, let me take a look at this. We could also write this way. This is another way to write this, okay? Okay, either way, it doesn't matter, right? Now, I'm going to write the equilibrium constant for this equation. Same thing as before, products over reactants. However, since this is for water, I'm going to use a little W instead of a C or an EQ, okay? So we're going to have KW, which is going to be called the auto ionization product of water. Just like before for equilibrium constants, what do we have? We have products over reactants, concentrations of products, that's H plus, and OH minus over reactants. But when we have a reactant, we have a liquid, you leave it out, right? So this is it right there. That's K equilibrium for water. KW again. It's called the ion product constant, okay? Sorry, having a brain meltdown there. Okay. Now I told you also earlier, I said at 25 degrees Celsius, each one of these is 1 times 10 to the minus 7. Molarity. So KW ends up equaling 1 times 10 to the minus 14. At 25 degrees Celsius. Okay, the temperature will change that a little bit, but we're usually going to use that right there. KW equals 1 times 10 to the minus 14. All right? Again, this is all at 25 degrees Celsius. Now, if we have a solution, the H plus concentration equals OH minus, Remember, I could also use H3O plus here. The H plus is actually attached to H2O molecule, H3O. So I can put H3O plus there, it's the same thing. Either way, it doesn't matter. When these two are equal to one another, we have a neutral solution. If the concentration of our H plus is greater than our concentration of OH minus, well, guess what? We have an acidic solution. And surprise, surprise, if the concentration of OH minus is greater, we have a basic solution. Okay? Let's see here. I have a sample exercise here. What am I looking for? Hold on one second, sorry. Let's take a look at this. Take a look at practice exercise 16.5 on page 660. Now when I had KW, let me just quick write this real quick. Okay. KW is always going to apply. So if I have an acidic solution, the H3O concentration is greater than OH, we can use the value for KW, we can use the value that we have for the acid to get the hydroxide, or vice versa. Okay? I'll show you how this works in example 16.5 actually. Calculate the concentration of H plus when the OH minus concentration equals 2 times 10 to the minus 6 molarity. Right? This is actually pretty easy. So we have our KW equation. Right? Well, we have KW. KW is always 1 times 10 to the minus 14. Okay? So we have the OH concentration. We want the H plus. What are you going to do? Divide through by the concentration of OH minus. Right? I'm going to flip this around. And there you go. Just like that. Okay? And then plug in your numbers. And I forgot my calculator. But, I think this is going to turn out to be, sorry, let me think here. Five times 10 to the minus 9 molarity, okay? Well, KW normally doesn't have any units, right? This is molarity, but just stick molarity on there, right? I think I got that right. You might have to check my math to make sure I got that right. And actually, I'm going to go grab my calculator.